So are there any questions? Okay, so then let me start. So today, so far what we were discussing is two-dimensional, one-dimensional finite element formulation, and today I am going to start two-dimensional finite element formulation. So here what we are saying basically that whatever when you say two-dimensional, meaning is that whatever dependent variables are there, so the dependent variables are only are rather functions of, so dependent variables are unknown functions of basically two physical coordinates. Say for example, xy. So 2D means we have problems where there are dependent variables and they are unknown functions of two coordinates. Like in 1D we had no dependent variables which were functions of only one unknown coordinate, whereas here they are functions of two unknown functions of two coordinates, that is independent coordinates x, y here. And so now if you look at this, since the dependent variables are functions of two independent coordinates, so we need to discretize a two-dimensional domain. So here now the discretization would be, the FE discretization is going to be two-dimensional. So the discretization of two-dimensional domain, so let me just say that 2D domain. And when we talk of this discretization of two-dimensional domain, so domain can actually be arbitrary. So let us say that we have this as a domain for the problem basically has to be solved. And discretization means then we are dividing this into smaller subdomains. So this is a 2D domain, and the discretization can be, now when you talk of discretization, so the discretization again now in 2D, see 1D, of course some of the textbooks you will find also there is a formulation in natural coordinates, so it is just the transformation of the coordinates, but we will see here in 2D that for more general physical shapes of the element, formulation in natural coordinate actually space is essential to satisfy the continuity of primary variables across the element boundaries. But nevertheless, it is also possible to formulate the problem in physical coordinates. So here you will find that the formulation can be in some restricted sense can be in physical coordinate space. Of course, the general formulation would be in natural coordinate space. So the formulation again here is in physical coordinate space. So this is when I say formulation is more of actually the interpolation of the dependent variables, so physical coordinate space or natural coordinate space. We will, when we actually continue, I will define what is natural coordinate and natural coordinate space and how we do that. But for the time being, so let us say if we are looking at physical formulation in the physical coordinate space, so then what is the kind of elements you can think of? So when you are discretizing, let us say this domain, the simplest geometry you can think of for dividing this into smaller subdomains is triangle. So I mean the simplest element shape would be a triangle with straight edges, and you can actually in a certain cases you can have just node at the center, but most of the time we have at least a 3-noded triangle. So let us say we have 1, 2, 3 as the local node numbers of a triangle. So this is the simplest possible subdomain, find that is subdomain we call as finite element. So this is the simplest possible shape you can have, and so obviously for this, when you are assuming the approximation or the interpolation for the dependent variable, let us say that now we have temperature as the dependent variable, and now this is a function of x and y, that is two coordinates, Cartesian coordinates. So this can be in that and let us say that we have for the time being, although we have not seen that what should be the degrees of freedom at the nodes of the element and what should be continuous across the element boundaries. We will see when we look at the differential equation and primary and secondary variables. But for the time being, let us say that we want to have the value of the t itself as the degrees of freedom at these nodes. So that is say t1 here and t2 here and t3 here. Then you can assume as an approximate solution for t as a0 plus a1x plus a2y. This is what you can assume as an approximate solution within this three-noded triangular element, where t is your dependent variable and it's a function of two independent coordinates, that is x and y in this case. Now, so if you look at here again, we have first is a constant term, then we have a term linear in x, term linear in y. So in the sense that you can say that you have a constant and linear terms. So it is basically a complete polynomial up to linear terms in x and y. And in addition to, so it's a complete polynomial up to linear terms in x and y having a constant term. And also we will see that the form of this interpolation remains same if you interchange x and y. So if I replace x by y and y by x, still I have no linear constant term, a linear in x and linear in y. So this property is known as geometric invariance. So in addition to whatever we had discussed for 1D, this also should satisfy what is known as geometric invariance. Geometric invariance means if you interchange x and y, form of the interpolation should remain same. Means is if x and y are interchanged, even then the form of interpolation remains same. Interpolation remains same. Okay. So in addition to a constant term, complete polynomial, we also should satisfy the geometric invariance condition when we are assuming the approximate solutions for 2D and 3D problems. So as of now we are discussing 2D. So this is the simplest shape you can think of using for discretization of the domain, the complete domain. Then you can then what you can do is next level of approximation you can have. So this linear in x and y, then you can think of say 3-noded rather than 3-noded. You can have introduce the mid-side nodes. So like we talked of linear truss element and quadratic truss element, that is with 3 nodes. So here if you have let's say the side nodes, also mid-side nodes. So these are, let's say, corner nodes, local nodes 1, 2, 3, and then this is 4, 5 and 6. And so, and again if you have the same kind of degrees of freedom, that is t1, t2, t3, so you would be able to assume approximate solution for x and y in this case as a0 plus a1x plus a2y and then plus quadratic terms, so say a3x square plus a4xy plus a5y square. So now you are having constant term linear in x and y and then the quadratic in x and y. So this is like x square, y square and the xy. So this is definitely going to be in terms of accuracy and convergence. This approximation is going to be better than this approximation because that's just linear, whereas this is quadratic. So we are assuming quadratic variation of dependent variable within the element if you are taking a 6-noded triangular element. So this is 3-noded triangle, this is 6-noded triangle. Quite often we typically use either if we are using triangles, either 3 or 6-noded triangle, although one can introduce then mid side node, so you can have 7 noded, 2 mid side, the center node, and then 2 mid side nodes, so you can have actually then 10 or 9 noded triangular element and so on. So but common ones are 3 noded and 6 noded triangular elements. This we are talking of the interpolation in the physical coordinate space itself. That is, you are approximating your unknown dependent variable in terms of your physical coordinates, xy coordinates, which is actually defining the physical domain of the problem. So then why only limit to triangles? You can also use actually quadrilaterals, but in the physical coordinate space we are not able to, we are still within this the physical coordinate space. We will have to keep this in mind. So now if you think of basically quadrilateral, so in formulation in physical coordinate space we are only restricted to actually rectangles. So then next to the triangle we can have a, let us say, a rectangle, and rectangle means obviously you should have at least 4 nodes. So these 4 corner nodes, 1, 2, 3 and 4, and you have no xy coordinates, so this is x and this is y, and here the sides are parallel to basically these x and y. And for the same variable here, t of xy, if you have only t as the degrees of freedom at the nodes 1, 2, 3 and 4, so you have 4 unknown temperature parameters or the variable parameters within the element, so you can have an approximate solution which has 4 terms in it. So you can have a0 plus a1x plus a2y, you should have a constant term, you should have linear term, and then what next? So we, as of now, we have only 3 terms. We need to add one more term. So what should be that? Should it be x square? Should it be y square? Or should it be xy? Why should it be xy? So that it is geometrically invariant. So that is a3 into xy. Now if we add a3 into x square, and if we interchange x and y, the form of the interpolation is going to change. That is, it would become, see, if you have x square, in one case it is higher order in x, and if you interchange x and y, then it will become higher order in y. So that's not desirable, because then you are giving actually emphasis to one particular direction, that my temperature field is varying with a higher gradient along the or with a sharp variation along x direction or along y direction. But when you formulate a finite element, unless and until, of course, you can always formulate a problem for a specific case wherein that the variable is varying with a higher degree variation along one direction and with a lower degree variation along other direction, then you can formulate that kind of a element. But for a general case, it should be geometrically invariant. So this is what you will take as the interpolation here for the 4 noded quadrilateral element. And so like then you can think of maybe 8 noded and 9 noded rectangular element. So there, this angle is still I am saying the edges are parallel to x and y that I am going to just answer. So say then you can have a, let's say, 8 noded rectangle, so 1, 2, 3, 4, and then the mid side nodes of 5, 6, 7 and 8, these are at the mid sides. You can then of course add at the center, so you can have 9 noded and so on. And now if you are choosing the polynomial for this case, t of xy, that would be a0 plus, now assuming that again the primary and secondary variable require that t is only the degree of freedom at the nodes of the element. So here 8 nodes are there, we will have 8 elemental degrees of freedom, so we must have 8 terms in the approximate solution. So a0 plus a1x plus a2y and then plus a3, obviously constant, then linear terms, then quadratic terms, a4 say xy, a5 y square. And now what should we have next? So it should be geometrically invariant. So once we have exhausted the quadratic terms, then we go to cubic terms. So say again there is a possibility of using x cube and y cube, or the combination of x and y, so x square y and xy square. So what we choose is x square y plus a7 xy square. So this is also geometrically invariant, and then you are choosing if you are using x cube and y cube, then you are missing terms which is no quadratic in x, linear in y, or linear in x and quadratic in y. So we prefer to first use all the terms which are of lower degree variation and then include the higher degree variation term. And for this, so this is kind of you can formulate the elements either triangles or rectangle only. That means these angles have to be 90 degrees in the physical coordinate space. So this is what you can do, formulation in physical coordinate space. And to look at this, we have something called what is known as Pascal's triangle. That is how we choose the terms. So in Pascal triangle, I mean, you can just look at how we have written all these terms. So at the top you have constant term, then linear term x and y, then quadratic terms x square, xy and y square. So that is like for the triangle we chose the first three, then for the 6 noded triangle we chose the first 6 terms, and then third degree terms of in x and y. So you will have x cube, x square y, xy square and y cube. So when we are choosing the terms for this 8 noded rectangular element, we are basically as you see, we are from this triangle we are basically choosing these terms here up to this. So we are not going for x cube and y cube. So if you are going for one more term, let us say that you want to formulate a 9 noded rectangular element, and in that case you will go for the next level of terms. So you can think of what to do. I'll just pose a question. So let us say x power 4 x cube y, and then you will have x square y square, and then you will have x y cube and y power 4, like that you can write. So constant term, linear, quadratic, cubic, quartic, quantic and so on. And now let us say that you wanted to add one more node to this element, that is instead of 8 noded you want to have a 9 noded element with the 9th node at the centroid of the this element. So in that case, which term will you choose? You will have to add then one more term in this approximate solution. So which one will you choose? So then obviously it should be geometrical invariant. So what we have actually this as a choice. So you will use then in addition to these 8 terms, you will use the 9th term as x square y square. So plus 8 into x square y square. So this is how we will choose the approximation of the field variables within the either triangular or rectangular elements formulated in directly in the physical coordinate space. Then why we are restricting this, another question is, before I move further, why we restrict to this? See, for example, now if I talk of continuity of, let us say in this case t itself, so assuming that t is the only primary variable, and we have discretization of a domain, so we have certain, let us say, domain, and we are discretizing that into a, let us say this is a domain which is a bit more irregular, and you are discretizing this into a number of triangles. So say I discretize this into different triangles. So this one triangle, this another triangle, then you discretize into a number of triangles like that, and then you have say another triangle here. So like that, you want to discretize this, this is going up to here, and like that, you are discretizing this into a number of triangles like this, and so on. So that's how you are doing the discretization. You can just do a different fashion. So this is a discretization using triangles. Let us say 3-noded triangle. And now if I want to look at, let us say 2 adjacent elements. For example, let me just talk of only, let us say, these 2. So that is, one triangle is going something like this, another triangle is going like this. So this is these 2 triangles, and of course you have somewhere your coordinate x and y. Now if I talk of this particular edge which is common, that is shared by this element, let us say this element is ith element and this element is jth element. So continuity of t across the elements means the temperature when we evaluate from this element along this boundary from here to here, and when we evaluate the same T using this element from here to here, they must be same. That is what is the continuity meaning now in 2D. See, in case of 1D, if the variable was same at a node, at a point basically in 1D, then we call say that the inter-element continuity or compatibility is satisfied. Here we require no continuity of primary variables across the boundaries, so in this case like along this line. And see, within each of these elements we are assuming the temperature to be linear. So say for example, temperature within the ith element, so for the ith element you are assuming T to be A0. Now let us say that the constants are in general going to be different for these two elements. So A0 Ix plus A1 Iy plus, sorry, I wanted to write it as A0 I plus A1 Ix plus A2 Iy. So this is the approximation within the first element. If you look at approximation within the second, that is jth element, T would be equal to say A0j plus A1jx plus A2jy. This is how the interpolation in general, these constants A0 for the A0, A1, A2 for the ith element and constants A0, A1, A2 for the jth element would in general be different. And now if we want to evaluate this temperature say from the ith element along this boundary, so this is a straight line, and this straight line equation would be, this is a straight line, you will have some equation. So let us say that the equation of this straight line is some A0, capital A0 plus let us say capital A1 into x. Either you can write y in terms of x or x in terms of y, because when we go from this point to this point, we are going along a straight line. The equation of a straight line is obviously along a line you cannot vary x and y independently, but one would be dependent on the other. So you can write say y equal to A0 plus A1x. When you do that, so that means when you are evaluating this temperature along this boundary from this, what you are going to do, you are going to write this as A0 I plus, now you are writing y in terms of x, so you will have A1 I x plus A2 I into y is your basically A0 plus A1x. When you are evaluating for this, you will have A0j plus A1jx plus A2j into y, that y is A0 plus A1x for that boundary. Resulting expressions if you look at, so now you see, you can, if you look at this one, so you have now, if you look at the constant terms, so you have A0j and plus you have A2j into A naught, this is a constant term, plus if you look at the linear term, so you have this A1j into x, and then you have here A2j into A1, so plus say A1 into A2j into x. So this is the form. Same thing you can actually write for this. So you will find that the temperature variation evaluated from the ith element along this boundary from here to here is linear in x. Similarly, the temperature evaluated along this boundary line from here to here from jth element, that is this element, is also linear in x, right. So the linear variation of temperature within the element gives rise to linear variation of either x or y along the common boundaries or a common edges of the elements. Like similarly, if you can have another, let's say jth and kth element and another boundary, you will always find that the temperature variation along common edge is going to be linear in x or y, depending on whether you express y in terms of x or x in terms of y. And we are already saying that the temperature values at these are the common nodes. So this is a common node here, this is a common node here, and we are going to have the same, we are going to enforce the same value of T for this node, whether it is belonging to ith element or it is belonging to jth element. So T for both the elements, whether you come from the ith or from the jth at this point is same. From this point also at this particular node, from both the elements it is same. So what then you are saying that the temperature, whether you take this, come from this element, at this point you have same temperature, where you come from this side you have same temperature, and here also whether you come from this side or this side you have same temperature. In between the variation is linear in either x or y. So once the temperature at these two nodes is same from both the elements and in between the variation is linear, that variation has to be same from both the elements, isn't it? Because it's a linear fit along that edge having same values of t at this location and this location, whether you are talking of this element or you are talking of this element. So once you have same value of t at this particular node belonging to both the elements or this particular node, and then the linear variation is obviously going to be unique. So what it means is that there is going to be continuity of t across the element boundaries, across the element edges for this particular case. If you have a let us say a 3-noded triangular element with linear variation of field variable or the dependent variable within the element. So that means you are able to satisfy the continuity of t across the element boundaries or across the element edges. Now similarly you can argue out if you take 6-noded quadrilateral. For example, now I'll just explain here itself. So if you now talk of a 6-noded triangle, say first this triangle, we have this as an approximate solution. Still the triangle is having straight edges. That means when we go from one, say now rather than sorry, let us say that no, these elements rather than 3-noded triangular elements, they are actually 6-noded triangular elements. So if they are 6-noded triangular elements, so I will have say one element going like this and another element sharing the common boundary will be going like this. Here I will have 6 nodes like this, and here also I will have 6 nodes like this. These 3 nodes are common to both these elements, and the temperature variation within each is assumed to be quadratic. And now this is again a straight line. Now the common bound edge shared by this element and this element is a straight line. So equation of this line would still be the same, y equal to say a0 plus a1x. And now when you substitute this in your approximation for the solution within each element, so that is expressions like t equal to a0 ix, a0 plus ix, a0 plus a1 ix plus a2 iy plus say a3 i x square plus a4 i y square, I mean you can write in any manner, a5 i xy. When you are writing this, same thing for the so this is the ith element and this is the jth element. So when you write this, now substitute this, that means what you are trying to evaluate the temperature, this t variation of t along this edge, from here to here. Along that y is a0 plus a1x. We are moving along a straight line. Two coordinates are not independent. When you substitute here, and finally we will find that the resulting expression would be quadratic in x, because this is anyway going to give it's already constant, this is linear in x. This will give a, when you put y equal to a0 plus a1x, will give you a constant and a linear in x term. This is already quadratic in x. This is when you write y square as a0 plus a1x whole square, will give you a constant term linear in x and quadratic in x. When you take this product, x into y again will give you constant term in x, term in x and x square. So overall you will see that after this substitution here, the resulting expression would be say a quadratic in x. Let me write that in terms of simply b0 plus b1x plus b2 x square, where b0, b1, b2 are going to be in terms of these constants and capital A0 and capital A1. And again see, when we are formulating this element, the quadratic triangular element, we are ensuring at the time of assembly that the T values, temperature values from this side and this side are same for this node. They are same for both the elements from this side at this particular location. Similarly, this node is common to both, having same temperature values. So I am going to say that this node of this element has same temperature value as that of this node of this element. Similarly, this node belongs to both, having same temperature value. So that means already through the assembly process we are going to enforce that temperature value is same for this node belonging to both the elements here and here. So at 3 locations we are forcing that T is same for both the elements, that is at this location and these 3 locations. So that means at 3 points through the assembly process saying that the common nodes of the elements have same temperature values, you are forcing already that at 3 points the T value from both nodes actually elements is same. Now and in between the variation, that is when you go from here to here, in between variation is quadratic for both the elements. Although so if for both the elements it is quadratic, that means this has to be again the values are same at this point, at this point, and this point, and in between the variation is quadratic. You can only fit a unique variation, quadratic variation. So that means irrespective of whether you evaluate the temperature variation from this element along this line or from this element along this line, the temperature variation will be actually same the moment we enforce that the temperature is same at these 3 nodes. So this triangle, 6-noded triangle formulated in physical coordinates xy coordinate space also satisfies the continuity of T in this case if T is there as degrees of freedom at the nodes of the element, and enforcing the continuity of first the values of T at the node points, and then it will also be same at along the entire edge. Now let us say coming to the rectangular elements, this 4-noded rectangular element. This is again I am saying here that the basically the edges of the rectangle are parallel to x and y. So this is my x and y. X and y in this case I am not essentially forcing it to be at the first node, although it can be. So let us say this is 1, this is 2, this is 3, this is 4. Okay, and the temperature variation we have already seen. Having for this particular case T was A0 plus A1x plus A2y plus A3xy. Now I might have this one element adjacent to this, there would be another element. First we will already be enforcing that T is same for all the elements connected to this node here, all the elements connected to this node here. So this point and this point, if I have element this side, the temperature values are same, the field variable values are same. Now if I look at now, since this edge is parallel to y, that means x is constant, so that means in this expression if you put x is equal to constant, it would be linear in y. If it is linear in y, it would be linear in y for this element as well as for the adjacent element. I have not discussed that element here. And if it is linear and the values are same at these 2 points, in between a linear variation means it would be unique. It would be same whether I evaluate that variation from this element or I evaluate it from the adjacent element. So again we would be able to satisfy continuity of the field variable, the dependent variable across the common boundaries, common edges shared by the elements. But now let us say I had specifically said that we have to have, if we want to have this quadrilateral type, means it has to be rectangle to satisfy this. Now let us say rather than talking of a rectangle, if I make one of the edges as let us say a quadrilateral, a general quadrilateral, let us say like this, let it be even be like this, and now see this is x and this is y. So this is one element, and we have 4 corner nodes for this element, and let us say you will have another element like this and something like this, another element. So this is like your ith element and this is your jth element, and these are the additional nodes. Of course there would be elements this side, there would be elements this side, and so on, isn't it? Now if you look at, still we have one node here and one node here. We are going to force that value of T for this node belonging to this ith element and this node belonging to jth element, the value of T is same. So I am going to say that value of T at this node, whether it's belong to this element or belongs to this element, is the same way here. So the value of T here and here is same. And in between, now if you look at the equation of this line is, if it is a rectangle with edges parallel to either x or y, so then either you are moving along x equal to constant, or you are moving along y equal to constant. But in this case again, let us say y would be something like a0 plus a1x. You are moving along a generally straight line, without x or y being constant. So then y would be a linear function of x, or x would be linear function of y. And when you substitute this, you look at the argument. So when you substitute this y equal to a0 plus a1x in this expression, the first would remain a0 and then a1x, and this will become of course a constant term and linear in x. But you look at this term, that will give you actually a quadratic in. So overall, when you put in this xy, this y equal to a0 plus a1x, actually the resulting expression would be quadratic in x. So what it tells you is that if this edge is not parallel to the common edges shared by the elements are not parallel to either x or y, and it's a 4-noded general quadrilateral with 4 terms in the approximate solution, then the temperature variation along the general common edges is going to be quadratic. Now if it is quadratic, so what it means is, of course through the assembly process you are saying that no, that at this point, whether it is this point belonging to the first the ith element or jth element, t is same. So I have the same t value here from both the elements. I have the same value of t from both the elements at this point. But in between it's a quadratic variation. If it is a quadratic variation, then see it can have a different variation from this element, it can have different variation from this element, because now quadratic means 3 constants. The third constant would depend on actually the values of temperature here, and for this element the values of the third constant would depend on values of the temperature there, and they in general would be different. So now you will find for this kind of a situation with the same approximate solution within the element, you will find that the temperature variation, although it would be temperature would be same here whether you evaluate from this element or this element, similarly it would be same here whether you evaluate from this side or this side. But in between you will find maybe from the ith element the temperature variation might be say something like this. If I plot that temperature along the length, so maybe from the first element let us say that temperature is going to be something like this. So the first element is, let us say the temperature variation is something quadratic, so not linear. So maybe from the first element the temperature variation is, let us say, like this, and maybe from the second element the same temperature variation might turn out to be, although at this point and this point it would be same, but in between the variation might be like this. So you will have same temperature value evaluated from the ith or jth elements at these 2 points, but the in between from here to here, in between, one element is giving a different temperature distribution, second element is giving a different temperature distribution. So that means along the common edge the temperature predicted from both the elements is not same. That means the continuity of temperature is not ensured in this formulation. If you interpolate the field variables, in this case temperature, in physical coordinate space, considering a general rectangular quadrilateral element. So the use of actually these quadrilateral elements is formulated in physical coordinate space is only limited to rectangles. We can't do the we can't satisfy the inter-element continuity requirement of primary variables across the elements for general quadrilaterals, and that is where there is a need for the second one, what is known as I have listed here. The formulation is in natural coordinate space. We are going to discuss now the derivation of element level governing equations, assembly and so on, but first some of the basic concepts, the difference now when we go for the 2D elements, why there is a need for a different kind of interpolation space. We call it as natural coordinate space. So in natural coordinate space what you are doing, see first is we must it will be more complicated, because if you have mid-side node, so then you will also going to have, so if you look at the interpolation for 8-noded element case is now this, and say for example now if you consider this term where y square is there, So capital A naught plus A1x whole square, that will give you terms x cube. So you will have like along a common boundary, the temperature variation would be up to x cube. So a constant term, linear, quadratic and cubic term, whereas you have only 3 common nodes. So the question asked is, what if can be okay, it is not possible to satisfy the continuity requirement across the element boundaries, common boundaries, for the 4 noded general quadrilateral element. Will it be possible to satisfy considering 8 noded general quadrilateral element? It will not be, because for the 8 noded quadrilateral elements you have terms like I was saying this x into y square. So this will give you actually along a common boundary, which is an inclined boundary that is not parallel to either x or y coordinates, then the temperature variation is going to be cubic. And you have only, say for example, 3 common nodes, whereas the variation is involving cubics, that means 4 terms essentially. So again you won't be able to get a unique temperature variation from this side and from the another adjacent element if the edge is not parallel to x or y. As long as it is parallel to x or y, so either I put x equal to constant in this expression or y equal to constant, I get quadratic variation either of in x or in y. And since I have the temperature values same from both the elements at 3 points, I can fit a unique quadratic variation from both the elements, and it has to be then same whether I evaluate from the left side element or the right side element. So it satisfies the continuity requirement. So if you think of like that, 8 noded gives you x cube, that is up to cubic variation of the temperature along the edge. If you add more number of nodes in this, you will find that the variation of temperature along the common boundary would always be of higher degree compared to number of nodes, common nodes shared by the 2 elements along that boundary for general quadrilateral. So what is needed is, then this actually tells us that we have to interpolate the field variables or the dependent variables always in the actually rectangular coordinate space. So rather than now, because physical coordinates, it is not always possible to discretize the domain into rectangles, because if the geometry is irregular, we have to have, if we are going for quadrilaterals, they have to be general quadrilaterals, they cannot always be rectangles. So then what we do is we introduce another space only for the interpolation of the field variables. We call it as natural coordinate space. So natural coordinate meaning is this varies from -1 to +1. So now for the two-dimensional case, you talk of a space, let us say, I am going to use the notation xi and eta for these coordinates. So let us say I have a xi and eta. One, like instead of x, I am using a coordinate xi. You can use r and s or whatever you want. Another, because two-dimensional space means I will have to use 2 coordinates. So another is eta, they are orthogonal to each other, but they vary from -1 to +1. So this natural coordinate space is just defined between -1 to 1 +1. That means essentially a square of sides 2 by 2. So that is, then if you look at the domain by this, it's just a square of 2 by 2. So since this coordinate is going to be -1, -1, this is going to be 1 and -1, this is going to be 1 and 1, and this is going to be -1 and 1. So this space is called as natural coordinate space. That is essentially space defined by natural coordinates, and natural coordinates are the coordinates which vary from -1 to +1. So then this space is always going to be square of side 2 by 2. And then what we do, so now this is a natural coordinate space. Our actual problem is maybe the physical domain like this plate or maybe this screen or any other geometry. That's a physical space, in actual dimensions, actual size of the problem domain, whatever. But now you are doing the interpolation in this particular domain. So rather than assuming temperature in the physical coordinate space x and y, you will assume the temperature in terms of these natural coordinates. And in the natural coordinate space, these are always the element edges are either parallel to natural coordinate xi, or the element boundaries are parallel to natural coordinate eta. I mean either of these 2 directions. and this formulation is known as actually formulation in natural coordinate space. And here again you can think of let us say a 4 noded rectangular element, or no general quadrilateral now in the physical coordinate space, but a square in the natural coordinate space. So now when you do the interpolation, you can have a general quadrilateral. So in the physical coordinate space, it's a general quadrilateral, say xy, and it's 4 noded. So let us say this is 1, this is 2, this is 3, this is 4. This element is actually in the physical coordinate space, but for the interpolation purpose, you are mapping this space into a natural coordinate space of no size 2 by 2. So this is xi and eta. There is a corresponding to this node, there is a node here 1, there is a node here 2, there is a node here 3, there is a node here 4. So every point here is mapped to a unique point. So let us see, if I have a point here in the physical coordinate space having coordinates x and y, this will have a corresponding unique point in this natural coordinate space. So this is 1-to-1 mapping. You call it as 1-to-1 mapping. So you have now what you are doing, you are having a physical coordinate space, and now element which is general quadrilateral here in the physical coordinate space, but this element is mapped to a square in the natural coordinate space, and then you assume your approximate solution rather than in terms of x and y in the physical coordinate space. You assume the temperature T as a in terms of xi and eta. So say you will assume it to be A0 plus A1 xi plus A2 eta plus A3 into xi eta. And always you will find that all the elements, so if I have another adjacent element here, maybe another general quadrilateral like this will be again mapped to a similar kind of element in the natural coordinate space. So the common edge, for example this 2 3 is going to be this 2 3 here, along with xi is constant. So xi is constant means then the temperature is only linear function of eta, and at these 2 points the temperature from both the elements is made same, and in the natural coordinate space is at this point and this point, in between the variation is linear. So obviously it would be unique from both the elements, so that it is the left side element or the right side element. And like that, when we will formulate go into detailed development of the element level governing equations, we will see this in more detail. But then now you will see your element in the physical coordinate space can be a general quadrilateral element. When you do the interpolation of the field variables, in this case temperature, in terms of natural coordinates, that is xi and eta, that is in natural coordinate space. We call this as master element in the natural coordinate space. So all the elements in the physical domain, which could be, as specific cases could be rectangle or can be general quadrilaterals, are all mapped to squares in the natural coordinate space. So the continuity of primary variables is always ensured if you actually do this formulation, and that is why there is a need for formulation in natural coordinate space for 2 and 3 dimensional problems. So you will find 1 dimensional problems you can either do using physical coordinates the way we derived, assuming polynomials in x and then develop the element level governing equations, or even you can do that in the natural coordinate space. Is actually not a mandatory requirement, but you see here, if I want to have arbitrary shaped elements in physical coordinate space, and then I have to have the formulation or the interpolation of the field variables in the natural coordinate space. And of course, so once you do this, so in addition to the dependent variable t here, because you are mapping a point here in the physical coordinate space to a corresponding point in the natural coordinate space, you will also be interpolating your actually independent variables, that is x and y. Now x and y also have to be related to xi and eta. So t is related to xi and eta, each point xy here. So if I have a point xy here, this has to be related to a corresponding point xi and eta in the natural coordinate space. So there must be a relationship between xy and xi eta also. So then we also have to express x and y in terms of xi and eta, so that if I know a point here, I can find out the corresponding point here, or if I know a point here, I can find out the corresponding point here. Because ultimately once you are interpolating the field variable in terms of xi and eta, so if I ask you that within the element I give you the values of temperature T1, T2, T3 or T4 at these 4 points, and then I ask you to find out value of temperature at some point in between. So of course I give you these coordinates, that the coordinates of this point are, let's say, xp and yp. So first thing what you will need to do is, corresponding to this point, you will have to find out the corresponding point here in the natural coordinate space. That is, corresponding to this point there will be certain values of xi and eta. So first you find out those values of xi and eta, and then put here in this approximation, you get the temperature value at this point. So we need to have a relationship between x and y, xi and eta also, in addition to this interpolation of the dependent variable. So this is referred to as formulation in natural coordinate space. Yeah. No, but then you can do that for one element, but then what about the next element? So because this has to be satisfied across all the common edges shared by different elements. So maybe if you have just two elements, one can do that, but it won't be possible for no assembly of such elements. So for a general case, then obviously we have no choice but to do actually the formulation in natural coordinate space. So again in this, since we need to also relate xy with xi and eta, so it's kind of interpolation of xy also in terms of xi and eta. So now we have interpolation of one is the independent coordinates x and y, another is the interpolation of your dependent variables, that is unknown temperature in this case. So depending on what kind of interpolation you use for your xy coordinates, which are describing the geometry, relating the geometric coordinates of points in the physical space and the natural coordinate space. And so if you use higher order interpolation for coordinates and lower order interpolation for the field variable, then it is known as actually super parametric formulation. If the same kind of interpolation, same order of interpolation is used for both xy and temperature or the field variables, then it is known as isoparametric finite element formulation. And if you do the other way around, that a lower order interpolation for xy and higher order for the field variables or dependent variables, then it is known as subparametric formulation. Again, most common one is isoparametric formulation. So when we discuss, we'll actually talk about in more details about the subparametric, isoparametric and superparametric formulation in natural coordinate space. So this is about now what kind of different elements you can think of, and of course as I said, the natural coordinate space, the element can be 4 noded, it can be 8 noded, 9 noded, 12 noded, 16 noded, 25 noded and so on. Most common ones are again basically 4 noded and 8 noded or 9 noded elements. So these are most commonly used. If you look at the packages, mostly you will find 2-dimensional elements which are either 4 noded or when you are talking of general quadrilateral family in the physical coordinate space, so either 4 noded, 8 or 9 noded. These are the most commonly used finite elements. So the next is we look at, so I'll again take specific applications and then discuss about the formulation in natural and physical coordinate space both. So the first problem I am going to take is 2-dimensional heat conduction. So 2D heat conduction. Yeah, these high and eta are referred to as natural coordinates, varying from -1 to +1. No, we always leave the interpolation in this form itself. So, but we have in addition to this, we have the relationship between x, y, xi and eta also. But the transformation is possible. Yeah, it is possible. Yes, it is possible. So now I am going to take this example on 2D heat conduction. And so first, obviously, we need to look at what is the governing differential equation. So the governing differential equation is, let us say you have for the timing, let us assume that the entire domain is a rectangular domain, and with say this my x here at one corner and this is my y, and these are say the sides, so this A and this is B. So first we need to develop the element level governing differential equation. So for that what you do, you actually consider a small differential element and draw its essentially the energy input and output to this. So if you draw the energy balance for this, so what you will have is maybe I'll just briefly discuss and then continue in the next class. So let us say that along this edge heat entering per unit area is say Qx, and along this edge the heat which is leaving out is Qx plus delta Qx. Similarly along y, let us say heat entering is Qy and heat leaving out is Qy plus delta Qi. Then also let us say there is a heat generation within this, which is per, let's say per unit volume. So this is Qg is the heat generated per unit volume, and say the thickness here is h. So let me say that the thickness is actually h. So how do we now, let us write then, and assuming that it's a steady state problem. So 2D heat conduction is steady state condition. So I am not considering transients. We will look at the transient problems later when we are through with some of these basics. So now if I write the energy balance, so you see that this Qx is the heat per unit area which is entering into this volume, and this is the heat which is leaving. So if I write the energy just leaving out, that is going to be this term and this term. So due to this is going to be delta Qx, that's I am just only writing the energy balance, delta Qx into this edge area. So if this length is delta y, then this would be delta y into h. And if I look at same thing is entering, so minus that, this term gets cancelled, plus the heat leaving from this side is essentially this minus this, so which is delta Qy, and then this area which is going to be delta x into h. So this is the net heat which is leaving out from this element. This must be equal to heat generated within the element, because it's a steady state problem. So Qg is the heat per unit volume, so that is delta x into delta y into h is going to be the volume. So this is the energy balance, simple energy balance relation. Now we want to derive a differential equation. So what we do is we divide this whole thing by volume, that is delta x into delta y into delta h, and so the first term will get delta Qx divided by actually delta x in the limit when delta x tends to 0. So this will translate to del Qx by del x, plus the second term, if when you are dividing it by volume, that is delta x into delta y into h, you will get delta Qy by delta y. When delta y tends to 0, that would become del Qy by del y equal to Qz. This is in terms of heat flux Qx Qy per unit area. Now we bring in, this is just the energy balance relation for the steady state problem. Then we bring in the constitutive relation, that is Fourier heat conduction law. So here for let us say linear isotropic material, linear isotropic material, you will have Qx as minus k into del T by del x, and Qy would be minus k into del T by del y. So area term is not coming here, because small Qx Qy are the heat per unit area. So simply minus k into del T by del x minus k into del T by del y. If you substitute this constitutive relation in this particular differential equation, what you will get actually is del by del x. So let me write minus sign here, k into del T by del x minus del by del y of k into del T by del y is equal to Qz. So this is your differential equation in terms of temperature T, the governing differential equation. When we solve problem, first we have to develop, say, the weak form of this differential equation, identify primary and secondary variable. Then we have to, based on that, have to assume an approximate solution within a triangular element or 3-noded or 6-noded triangular element or rectangular elements or natural coordinate space, and then we will have to develop the element level governing equations. So we will continue in the next class on the development of weak form and then the development of element level governing equations within the element for the various kinds of elements I talked about. Okay. So if you have any doubts or questions, you can ask outside.